Welcome back, everybody. So, as I said, we have no quiz today. I didn't get a chance to do it. So, we're going to continue moving on and chug away at the chain rule. So, once again, the chain rule is the derivative of the outside function evaluated at the inside. That's the f prime of g of x times g prime of x. Now, in practice, as we saw in this one, what ends up happening is you take the derivative of the outside function here being that 1/4 power, and then you evaluate the inside. So that's why it's 2 minus 9x to the negative 3/4. The derivative of x to the 1/4 is 1/4 x to the negative 3/4. But we're evaluating the inside times the derivative of the inside, which ends up just being negative 9. Now, as you get better and better at this, it becomes less and less needed. So, as another example, so let's look at this example here. F of z is equal to z to the fifth minus 1 times 1 minus 3z to the 2/3. Now, that is a product of two different things. So we have to do a product rule. And the whole point of this problem is to remind us that all the rules can get combined. So product rule, quotient rule, chain rule, all of them can be combined in one problem. You can have a chain within a product rule. You can have a product rule with a chain rule and a chain rule. You can do so many different things. So it's getting comfortable with all the different things. And so that's why I'm glad we studied that 2.3 a lot before this non-quiz. So I'm going to label it this time, but typically I'm going to avoid it. So f prime is 5z to the fourth, and g prime is going to be 2/3 times 1 minus 3z to the negative 1/3 times negative 3. Take a second to understand that. Take a second to see it. Because it's one of those ones, yes, you can appeal straight to the definition, but just like with a lot of them, the more, just like with the power rule and like the original rules, where it ends up being way more complicated if you try and do it each individually separately and try and like do all the work at once. Instead, doing it sequentially really makes it more efficient. So the outer function for g was the 2/3 power. That's why it's now 2/3 by a power rule to the 1/3. But you're evaluating at the inside, so that's why it's 1 minus 3z times the derivative of 1 minus 3z. And we can write that above it if you'd like. This is ddz of 1 minus 3z, the derivative of the inside. And so we can pretty that up a little bit, which I would recommend. So this is negative 2 times 1 minus 3z to the negative 1/3. So we have everything we need. We can use the product rule, f prime g plus g prime f. So capital F prime of z is f prime, so 5z to the fourth times g, which is 1 minus 3z to the 2/3, plus g prime, but it's going to be minus, so I'm just going to switch that immediately to a minus. It's a negative 2, so I'm going to switch to a minus. G prime, so 2 times 1 minus 3z to the negative 1/3 times z to the fifth. And we can leave it like that. The only time we want to simplify it is if we had to deal if we had to use it for something like finding where the tangent lines were 0 or undefined or something like that. That's when we would use a little bit of algebra to simplify. Okay? Any questions on that? We're going to keep practicing that chain rule. There's a lot of practice problems here. So this one is a guaranteed one that makes students get upset at first, and I can sometimes try and incorporate it. Sine to the fourth of x. Please remember that this is sine of x to the fourth power. Sine of x to the fourth power. So it's a chain rule. The inside function being sine of x, the outside function being the fourth power. So if this is my f and this is my g, then let's do f prime. The outer function is the fourth power. So the derivative of that by the power rule would be 4 blank to the third power. So it'll be 4 times sine of x to the third power times the derivative of the inside. The derivative of sine is cosine, which we'll write prettier as 4 sine cubed of x cosine of x. So I'll let people write that down, and then we're going to go back over that one more time because the chain rule is super, like, it's uncomfortable at first. It's like, but like once you get it, it's like riding a bicycle. Like you can just keep doing it. Yes.
Would you like us to make it pretty for the future?
No, don't worry about that unless it's needed in a problem. If you need to like factor it, if you need to do something, sure, simplify it. Otherwise, just leave it as the basic components. The only thing I request is simplifying nice algebra or arithmetic. Like if it's -2 times -3, make it a +6. If it's 4/16, make it a 1/4, and so on and so forth. So G prime is a quick power rule. G prime is 3x squared. So we have everything we need. So let's use Leibniz's notation, dy dx, because it doesn't matter. They all mean the same thing. So f prime was 4 sine cubed of x cosine of x times g, which is x cubed minus 8, minus g prime, which is 3x squared, times f, which is sine to the 4th of x, all divided by g squared. So x cubed minus 8 squared. And there we have it. Yes.
Why include cosine?
The cos that was from the f prime. F prime's derivative, because it's going to be a chain rule, because there's an inner function and an outer function. So the derivative of the outside function, the 4th power, is 4 blank to the 3rd power. And then you take the derivative of the inside, which is cosine. The derivative of sine is cosine. Is that all right? Let's do a couple more practice. Honestly, before we go into more complicated cases, let's add in an extra problem, D. Let's do someone give me a letter. X of t, capital X of t is equal to cosine of x squared plus natural log of x minus 7. All right, let's do that. All right. So this is, once again, a chain rule because it's an outer function, which is cosine, and an inner function, which is x squared plus natural log minus x, or natural log of x minus 7. So the outer function is cosine. The derivative of cosine is negative sine. So x prime of t would be negative sine of x squared plus natural log of x minus 7 times the derivative of the inside. The inside function being x squared plus ln x minus 7. So the derivative of x squared plus ln x minus 7 would be 2x plus 1 over x, and that's it. Any questions on that? So, outer function is cosine, inner function is x squared plus ln x minus 7. Chain rule says derivative of the outside function, the derivative of cosine is negative sine. Evaluated at the inside function, that's why it's negative sine of x squared plus ln x minus 7 times the derivative of the inside function. And so you can write that each time if you want. This is d dx. Dt. Oh, I don't know why it became x's. Let's change its name from x to capital G. And so call it g of x. Capital G of x. So capital G prime of x. And so that's a d dx of x squared plus ln x minus 7. Apologies on the mix up of variables. Okay. Any questions on that? Yes.
If there was like a time where you cosine parentheses and then that equation again, would you take the derivative of the inside after you've done like the both cosines?
So are you saying
Like it was cosine parentheses cosine parentheses x squared plus
excellent question. Excellent question. There is such a thing as a double chain rule or a triple chain rule or a quadruple chain rule. In fact, one thing I'm going to show you is a question that if you can get this one right, you understand the chain rule. This question was on my homework when I was taking calculus. This one right here. The square root of sine, of cosine, of tangent, of secant of x. So that is a chain rule within a chain. Let me highlight it. That is a chain rule within a chain rule within a chain rule within a chain rule. It is a frequent thing, and writing it down was the most monstrous thing because you had to write it down in WebAssign, and they only give you a box this big, and the box would not expand. So you had to keep you'd have to keep entering, but none of the stuff that you wrote before would show up. So you had to constantly check back and forth and make sure you wrote everything correctly because one wrong sign, one accidental parenthesis marked it wrong. I was a tutor when they kept that problem at the University of Washington. Now I was a tutor, and it got to the point where we were just like, just give me it. Like I'm going to type it in because I don't trust you. Like we'll go through the problem, but I'm not going to let you type that in. I'm going to do it myself because I trust myself. I don't trust you. So, anyways, this is a very good problem in understanding the chain rule. If you can do that one, you're pretty solid with your understanding of the chain rule. Question 4, highly recommend. It's a great way to build bonds with your parents. You do that with your dad, you'll have a grand old time. All right. So f of t equals sine of square root t plus the square root of sine of t. So there is a difference between these two things. One time it's sine of a square root function, whereas the other one is the square root of a sine t. So it's two different things. I'd recommend writing them in radical format. So I'm going to rewrite it as sine of t to the 1/2 plus the quantity sine of t to the 1/2. So that is two separate chain rules. The outer function for the first piece, the first term, the outer function is sine. The second term, the outer function is the 1/2 power. So f prime of t, the derivative of sine is cosine of t to the 1/2 times the derivative of t to the 1/2. So we'll even write that down, dt of t to the 1/2 plus the derivative of the outside function of the 1/2 power of sine of t. The outer function is that 1/2 power. So it'll be 1/2 sine of t to the negative 1/2 power times ddt of sine of t. Yes.
I'm sorry, I might have got lost here.
No, that's all right.
So in the beginning, the cosine t to the 1/2 power times the derivative t to 1/2. Like I thought 1/2 t to the negative 1/2.
That is what that is.
Oh.
So that please remember, like this is another way to write the same thing. This is taking multiple steps to get there. This is going to be 1/2 t to the negative 1/2 because it's saying the derivative of t to the 1/2. This is saying the derivative of sine of t. But if you want to skip writing that ddt and immediately write the answer, be my guest. That is correct.
Oh, okay. So you're saying it hadn't been like solved out.
I have not finished it yet. Yes.
Oh, okay, sorry.
So then finally, f prime of t is 1/2 t to the negative 1/2 cosine of t to the 1/2 plus 1/2 sine, bracket sine of t to the negative 1/2 times cosine of t. And that is your final answer. It looks uncomfortable, yes. And you could put the t in front. You could do cosine of t to the 1/2 times 1/2 t to the negative 1/2. Just make sure it's clear that it's being multiplied. And we're good. Okay. Any questions on that? Please ask questions. Because the chain rule is here to stay. It is going to be used a lot. Every single problem we do pretty much from here on out will involve the chain rule. Yes.
Okay, I might have been just going crazy. How come, like when I saw it the first time, I tried to, I thought it was the product rule for sine times square root of t. I tried something like that and messed up. Like, how do you like separate that?
So
Like, yeah, I would have thought.
for this one right here,
Yeah.
Well,
It was broken up that much.
excellent thing. Excellent. And I'm glad someone mentioned this because this is a very common mistake that students make is sine by itself. If you just say sine, that is an operator. It is an operation on something. That's why I mean, like I know some textbooks will do it. They'll do like sine t like that. I disagree with that notation. Personally, I like to write the parentheses because sine is an operation on something. So if you're trying to think of this as a product between a sine and a square root t, that's incorrect reasoning because because sine by itself is nothing. Sine of something, that's something. Does that make sense?
Yeah.
So sine always needs to be like any trigonometric function always needs to be attached to something. Same thing with natural log. Natural log needs to be attached to of something.
But if it was like a 5t
Yes,
sine, that would be a product.
yes. If it was e to the t square root t, then it's a product rule. If it was
Just trig.
sine of t times square root t, that's a product rule.
Oh.
Because that's sine of t times square root t.
Okay, that makes sense. Thank you.
That happens more than you think. Like that happens quite a lot, actually. That's an easy mistake to make. But sine, natural log, any of those things, they are operations on something. So, all right. Now, this one is a really, really good example of how the chain rule works because this is a chain rule within a chain rule. Because there's an innermost function, which is the w squared plus 1. Then there's another inner function that's slightly less inside. It's like the middle function of cosine. And then the outermost function is sine. So the derivative of h prime of w, let's use some Leibniz notation. Let's have some fun. dh dw. Yes.
Before we continue, there have been times where I do the exercise,
Mm-hmm.
and so then there are times where like the cosine is like first. You know what I'm saying?
Yes.
Does the order matter?
So, excellent question. The order does not matter because it's all multiplied together. It's commutative rules tells us that it doesn't matter which. Now, what I will say is that there's usually a convention in mathematics. The convention for how to write something is usually number, polynomial, then exponential / log, then trig / inverse trig. No, because it's all, it doesn't matter. It's just the convention to make it look pretty.
Yeah.
Like mathematicians have, like, we're bored, you know? Like, I mean, I as part of the reason why I knew I wanted to be a math major is I got obsessed with writing sigmas. Because I was like, I got to make my sigma look awesome. And that was before sigma became a thing, by the way. That was before you kids all said people are sigma or whatever the heck that means. But I got really, really interested in drawing a good sigma. And so point being, back to this, is mathematicians got very bored and we're trying to make sure it looked as pretty as possible. And the convention seemed to be that constants go first, then polynomials, then exponentials and logarithms, and then trig. And it doesn't matter, like exponentials and logarithms, they could be jumbled around. Trig and inverse trig could be jumbled around. But that's just convention. It does not need to be done that way. As long as it's all being multiplied together, it's all the same. So I believe in the answer keys that I have. I try to make sure it looks exactly as you would compute it instead of the way I would normally present it myself. Does that make sense? Yes.
Sorry, for exams.
Yes.
Do we have to like show the work of like
The DDT?
Yeah.
No.
We
no.
just write it all out.
You can just write it out. I'd like you to get, honestly, I encourage that because that will make you stronger and faster as a mathematician. The better, the faster you get at doing the chain rule, the better. This is just as a placeholder for now. Later on, we'll skip writing that unless people have questions about it, which is totally fine. So this next one has a really good way of showing how the chain rule works. So the outermost function, the derivative of the outside function is the derivative of sine, which would be cosine. So it's the derivative of the outside function evaluated at the inside function. The inside function for sine is cosine of w squared plus 1. So this is cosine of w squared plus 1 times the derivative of that inside. So times ddw of cosine of w squared plus 1. I took care of the first chain rule. Now I've got to take care of this chain rule. The derivative of cosine is negative, and we'll write this above it so we can make this look pretty. The derivative of this, outer function is cosine, inner function is w squared plus 1. The derivative of the outside function is negative sine of the inside, so w squared plus 1, times the derivative of the inside function, 2w. So at the end of the day, combining it all and making it look nice, dH dt is going to equal negative 2w sine of w squared plus 1 times cosine of w squared plus 1. And that's good. I just jumbled it around, yes.
So, the order of like solving derivatives like that.
Mhm.
So it's best to go like outside and then inner.
Yes, because that's how the chain rule operates. It's derivative of the outside, then times the derivative of the inside. I mean, I guess you could find the derivative of the inside and multiply that up front first. I suppose that is possible. It just looks more systematic when you do it the derivative of the outside first, because it's like f prime of g of x times g prime of x. It looks better that way, I guess. Okay. Yes.
So putting the negative in front of the 2w doesn't change like in how the answer is. It doesn't make it wrong.
Nope. So the reason why I did it this way, by the way, is I'll see students write this. They'll write cosine of w squared plus 1 minus sine of w squared plus 1 times 2w. What's the problem?
And it's not multiplication.
Minus not multiplication. So in order to do this, you need to put the parentheses around this. You'd have to put the parentheses around it. Like that. Yes.
Okay, maybe I will. If I put like how you had it without the parentheses, but I put like multiplication dot, would that have gotten marked, or do I have to put in parentheses?
That would not be enough, in my opinion, because that can be very, very easily misconstrued. All right. Any other questions on that one?
Yeah, I don't like the part that you deleted.
Say what?
I didn't understand the part that you deleted. Yeah.
So the derivative of the inside is this. But if you don't have parentheses, it now looks like and is read by any computer. This reads as cosine of w squared plus 1 minus the quantity sine of w squared plus 1 times 2w, instead of being multiplied together, which is what it is. So. All right. Next one is an e function. The e is the outer function because the inside is this. This is the, I mean, we can even highlight it if we'd like and say like, this is the inside function. So the outside function is e, and the derivative of e to the x is itself. So k prime of x equals e to the x cubed minus 7x squared plus 2 times 3x squared minus 14x plus 0, but I don't need to write the plus 0. That's one of the interesting things about e to the x. In fact, and you can even use this as a nice little tidbit. If I have y equals e to the f of x, then y prime is e to the f of x times f prime of x. Always. Because it's going to be the outer function is e. The derivative of e is itself. Evaluated the inside, so that's why I've got e to the f of x times the derivative of the inside, which is f prime of x. So that's what's happening here. Whenever you take the derivative of an e function, you always get back the original, like the original function itself. It's pretty cool that that happens. That's why we should celebrate E Day and not Pi Day. Yes.
So if it wasn't an E, it was like 5 or something,
5 to the
and then all that power,
Mhm.
we just move it in front of the 5 though?
Nope. Excellent question. So, bonus. What about y equals 5 x cubed, 5 to the x cubed minus 7x squared plus 2? So, JT has a very, very excellent point. Do I use the power rule here? Can I just bring this top part out front and then reduce the power by 1? And the answer is no, because the power rule only works for numbers. X cubed minus 7x squared, that has variables in it. So those things vary with time, with changes in x. So instead, the outer function here, I promise I know how to spell outer. Outer function is 5 to the x, which has derivative. If you guys remember, I don't expect you to because I don't have you guys memorize it. It's natural log of 5 times 5 to the x. So the derivative dy dx would equal natural log of 5 times 5 x cubed minus 7x squared plus 2 times 3x squared minus 14x. Let's talk through that after you've written it down. You understand where everything came from. The outer function. Wait. So I just love the chain rule. Get too excited.
That kind of problem be on my test.
I do not have you guys memorize the
That's
non-basis. If I did, I would give you the formula.
Oh.
So you need to know that and then know how to use the chain rule on it. So the outer function here is that fifth exponential function, that 5. And the inner function is x cubed minus 7x squared plus 2. The derivative of a non-e base exponential function is natural log of a times a to the x. That's way back when, but like once again, so the derivative dx of 5 to the x is ln of 5 times 5 to the x. That's what it is. But that's just the derivative of 5 to the x. We're dealing with the chain rule because we have not 5 to the x, but 5 to the x cubed minus 7x squared plus 2. So the derivative of the outside function, ln 5 times 5, evaluated the inside function. That's why it's 5 to the x cubed minus 7x squared plus 2, times the derivative of the inside function, which would be 3x squared minus 14x. Okay? Good. Oh, we have one right here. So, we could skip that. Let's make it something different. Let's do something more fun. Let's do capital T prime, T of y is equal to Let's do several chain rules. Let's make it pretty monstrous. Someone give me a function. Any function you can think of.
I think
Sine of another function.
See,
Secant. Ooh. Secant of what? Tangent. Let's expand our usage of other things. Let's use some non-trig functions.
Cotangent. Oh,
Close enough. What? The fourth root. All right. T to the 1/4 power times ln of t. All right. Do I have enough parentheses? No, there we go. And that's multiplied right there. So this is, if we look at it, we could even make this worse. Do we want to make it worse? No. We want to make it worse?
Yeah.
Yeah, let's make it worse. Let's make it worse. Let's let's do ln of t squared plus 1. Yeah. Let's do it. Have some fun. Okay. So that is sine of secant of t to the 1/4 times natural log of t squared plus 1. So that is a product rule on the inside of a chain rule, because there's an inner function and then there's another outside function. So this is two chain rules. So the derivative of this, t prime of y, and this is one of those ones where I might actually rewrite the ddys. I might write that down because it's a lot to work with. But the outermost function is cosine, or is sine. So the derivative of that would be cosine. So cosine of the inside, so cosine of secant of t to the 1/4 times ln of t squared plus 1 times ddy. Oh, why did I make it t's? All right, let's just change the name from T of capital T of T. Capital T of T. Sorry. I don't like using y as a variable if I can avoid it. ddt of secant of t to the 1/4 times natural log of t squared plus 1. So let's break it down. Let's make sure we understand. The outermost function is sine. The derivative of sine, the derivative of the outside function would be cosine evaluated at the inside function. The inside being secant of t to the 1/4 times ln of t squared plus 1 times the derivative of that function, that inside function. And now we have another chain rule. We have secant on the outside and t squared, or t to the 1/4 times natural log of t squared plus 1 on the inside. So start your function at the very, very left. So t prime of t is equal to cosine of secant of t to the 1/4 times natural log of t squared plus 1 times the derivative of secant. So we bastardize it and say the derivative of secant is secant tangent, but that's not correct. It's a quick way to say it, but it's actually the derivative of secant is secant of x tangent of x. So it's not secant of tangent of x, it is secant of x times tangent of x. So the derivative of secant, the outer function here, is secant of x tangent of x. So it's the derivative of the outside evaluated at the inside. So it will be secant of t to the 1/4 times natural log of t squared plus 1 times tangent of t to the 1/4 times natural log of t squared plus 1, then times d dt of t to the 1/4 times natural log of t squared plus 1. Whew. Yes.
So if you would have just put secant of t times tangent of t, that would have been wrong.
That would have been incorrect. So let's talk about that one, because that one's weird. Secant and derivative of secant and the derivative of cosecant, they're very strange. They're very strange because the derivative of it just as a moment, just writing up top. d dx of secant of x is secant x tangent x. So that means that d dx of secant of f of x is secant of f of x tangent of f of x times f prime of x. Let's write that down, and then we'll digest it again. That is just straight up grape nuts. No milk, no nothing. That is something that takes a lot. That's 5 saltine crackers right there, with no water at all. No water at all. I was trying to swallow a spoonful of cinnamon. Don't do it. Cinnamon challenge was great. I love when it came a thing. I tried it myself. It was terrible. Don't do it. So now that we've written it down, the derivative of secant of f of x, that is a chain rule because the outer function is secant, the inner function is f of x. So the derivative of the outside function, the derivative of secant, would normally be secant x tangent x. But remember, it's the derivative of the outside evaluated to the inside. So it's secant of f of x, tangent of f of x, times the derivative of the inside, which is that f prime. So we're going to do this. We're going to go t prime of t equals blah. And we'll just write this and go like that, because otherwise it won't fit. Unless you want to really start to tail it down the side, it's not going to work otherwise. But that is all there, right? And then there's a product rule where this is your f and this is your g. But lo and behold, there's a chain rule in the product rule. So we can write it above it if we'd like. F prime's derivative would be 1/4 t to the negative 3/4. And g prime is a chain rule. T to the 1/4 is fine. Doesn't require anything but a power rule. But g is a natural log function of another function. So the outer function is natural log. The inner function is t squared plus 1. Derivative of natural log is 1 over x, but it's not natural log of 1 over, it's not natural log of x, it's natural log of t squared plus 1. So it's going to be 1 over t squared plus 1 times 2t. Any questions? Any questions so far? This is a good problem. We are stronger mathematicians for it. And every once in a while, you got to push yourself. You got to do a deadlift, right? You've ever been to the done the gym thing where if you're plateauing with what they say, you just deliberately add on more weight and try and survive. Yes.
So that was one of the cases where if it's the trig function, it's of the inside, it's not a product. But now we're
Yes.
getting towards the product.
Yes, because the inside of the trig function, the final trig function secant, was a product.
Okay.
On the inside of the function, it's product. Any questions? So we got all that red stuff there times a product rule. So it's f prime, so 1/4 t to the negative 3/4 times g, which was ln of t squared plus 1, plus g prime, which is 2t over t squared plus 1 times f, which is t to the 1/4. And we can go take a nap. Secant and cosecant always have weird derivatives because of that fact that it's not we bastardize it because we want to stay things fast and we want to say that the derivative of secant is secant tangent, but it's really the derivative of secant x is secant x tangent x. Any questions on that? Okay. Let's see here. How many more do we have? 1, 2, 3, 4, 5, 6, 7, Okay, we got 7 more. So I'd like you guys to try B and C yourselves. Feel free to talk to your neighbors. I'm gonna walk around and then we'll come together in just a moment. So I'm gonna pause the recording. Back, and so here are the answers. So the first one, the outer function is natural log. Not natural log of x, but it's natural log of 7x to the 5th minus 4e to the x cosine x. So the outer function is natural log, the inner function is 7x to the 5th minus 4e to the x cosine x. So the derivative of a natural log is 1 over x, but in this case, it's going to be 1 over the inside because it's going to be a chain rule. So that's why it's 1 over 7x to the 5th minus 4e to the x cosine x times the derivative of the inside. Now the 7x to the 5th is just by itself. It's having 4e to the x cosine x subtracted from it. So we can take that thing's derivative really quickly. It's 35x to the 4th. But the next piece, the minus 4e to the x cosine x, that's a product. So there are 2 schools of thought when it comes to taking the derivative of that. You could either think of it, I'm going to erase this for just a moment so I can write above it. You could either think of this as negative the quantity 4e to the x cosine x, in which case you can use the product rule and do what I did. I treated the minus sign outside and then took the derivative of that by itself. And that's where I got, so for people watching the recording, I kept the minus sign outside and then took the derivative of this on the inside. Another way to think of this is of plus negative 4e to the x cosine of x. In which case you can do that and then you have them split apart and you're fine. It's all fine and dandy. It's your choice. I usually like to just deal with signs later if I have to. So that would be my recommendation, but it's not required by any means. So you have to do a product rule where the first function, luckily it's a nice product rule. There's no chain rules within it. But we could make it nastier and add those things. But f prime is 4e to the x. G prime is negative sine of x. That's why it's 4e to the x cosine x, f prime g, plus g prime. But g prime is negative sine of x. So that's why it becomes minus sine x 4e to the x. And then just writing it pretty, written like that. But you could probably leave it as is and I'd be fine with it. Any questions on B? C is a double chain rule because it's e of cosine of x cubed. So there's that 2 ofs. There's 2 chain rules. So you work outside to inside. The outermost function is e. The derivative of e is itself. So, but like the derivative of e to the x is e to the x. But this is e to the cosine of x cubed. So the derivative of e to the cosine x cubed, derivative e is e itself, so it's e to the cosine of x cubed times the derivative of the inside being cosine x cubed. That's another chain rule. The derivative of cosine is negative sine, so that's why it's negative sine of x cubed times the derivative of x cubed, which is 3x squared. And then you could write it prettier to write it as negative 3x squared sine x cubed. I guess I probably should have put this in front, but either way. All right, any questions on that? Now these other 2, these 3 actually, they are meant to remind us of something because we could go through and do it, right? We could do it the old-fashioned way and say, okay, well, the outermost function is natural log, and then it's natural log of this, so it would be a chain rule with a quotient rule on the inside. Yes, we could do that. Same thing here. We can rewrite this as a radical, and then we have a chain rule within chain rule. And this one, even worse, this would be a chain. This would be a chain rule within a chain rule with a quotient rule on the inside. And I don't want to do that because, and I don't need to do that if we remember props of logarithms. You guys remember those? No? Maybe so? No? Oh, unfortunate. So ln, or when we can do log base b of m times n is equal to log base b of m plus log base b of n. Log base b of m divided by n is equal to log base b of m minus log base b of n. And last but not least, log base b of m to the r is equal to r log base b of m. Those are the three big properties. There's more, of course, but those are the three big ones. That multiplication on the inside becomes addition on the outside, division on the inside becomes subtraction on the outside, and exponents become multiplication on the outside. Those are the three big rules about logarithms. I'm bringing them up now because they will play a role later. There's a thing called logarithmic differentiation that hinges upon this fact. So that's something to think of in the future. Those are those three big properties. And so instead of dealing with a chain rule with a quotient rule inside, I can split this up into two quick chain rules. By the properties of logarithms, well, I'll let you write those down. We'll write them down. It's a lot to write. We should remember our properties of logarithms. Logarithms are the coolest thing from Math 126. It's the best part of it. That's why functions is the best part of it, but either way. So that is division on the inside. It can be broken up into subtraction. So R of t could instead be rewritten as ln of sine of t minus ln of t squared plus 1, which are very quick chain rules, as opposed to a chain rule with a quotient rule is that. You would get the full credit regardless, but I'm going to write on your exam, if you do it the long way, I'm going to say, think about using the properties of logs. Make it a little bit easier on you. So that is R of t. Notice that's equal to R of t. So now I'm going to write dr dt. Let's use a little bit of Leibniz notation. Let's get comfortable with both. The outer function of the first term, the outer function is natural log. The inner function is sine of t. So the derivative of natural log is 1 over x, but this is 1 over sine of t because the inside is sine of t. So it's 1 over sine of t times the derivative of sine of t, which is cosine t, minus natural log of t squared plus 1. So the outer function is natural log once again. So it's 1 over the inside. So 1 over t squared plus 1 times 2t. And we could leave it like that, or we could make it pretty. We could because cosine over sine is cotangent. There we go. Good, good, good. I'm glad we all remember our trig. Glad we're all practicing our trig as we go along. But you could leave it like that and it's fine. Same thing with this one. Unless there's any questions on the previous one. If you're bored, go ahead and try and do it by chain rule only. Don't use the properties of logarithms. It's good practice. It looked different at first, but I guarantee if you simplify it, it'll give you the same thing. So the same the thing here, and it's of course, I had to do it. If you've had me before in a class, you know I love q as a variable, specifically for q cubed. It sounds too good to be true. Q cubed is way too fun to say. So I know you're all saying it in your head, q cubed. So this is c of q is equal to log base 5 of the square root of q cubed minus 4. That inside is q cubed. So that's going to have to deal with in a second. That q cubed, we're going to have to deal with that q cubed in a second. I just want to keep saying q cubed. It's too fun to say. But first things first, I want to rewrite this as q cubed minus 4 to the 1/2. That allows me to, instead of doing a double chain rule, right, because it's not like the log base 5 is on the outside, then there's the cubed minus 4 to the 1/2. Instead of doing a double chain rule, I can bring the exponent out and rewrite this as 1/2 log base 5 of q cubed minus 4. So that 1/2 is now a constant, and constant or a coefficient, and constant multiples, coefficients, they can be ignored. So C prime of Q is 1/2 times 1 over natural log of 5. Because this is not natural log, this is log base 5. And the derivative of log base B, and we can write this off on the side if you want, ddx of log base B of x is 1 over natural log of B times 1 over x. That's the derivative of log base B. I don't expect you to have that memorized because I'm not usually going to test on it. If any teacher decides to put that in your 182 classes, please tell them that Phil said they're a jerk. They'll know who I am. So pretty well known in the department as a troublemaker. So yeah, they'll know it was me. Tell them Phil thinks you're. I mean, you can use other words instead of a jerk. You can use something a little more vulgar if you wish. There's a couple people that I'd love to say that to. So go ahead. No, that's not true. Except for one. No, I'm kidding. 2. 5. Yeah, let's give it 5. No, I'm kidding. But anyways, so this is log base B, but it's not log base B of x, it's log base B of q cubed minus 4. So it's going to be 1 over q cubed minus 4 times the derivative of q cubed, and the derivative of q cubed minus 4 is 3q squared. And I'll stop saying q cubed now. And we can leave it as is, or we can make it prettier. Doesn't matter to me. Any questions on that? Yes.
Sorry.
No need to sorry.
We did the chain rule.
Uh-huh.
and Moved the 1/2 or the log base 5.
That's not the chain rule. That's the product rule of logarithms. The exponent rule of logarithms.
Oh, okay, never mind. Different.
That answers that. Okay, cool. All right. The last one, I'm gonna basically take care of it really quickly. That's to the 1/2 power. So this could be rewritten as 1/2 natural log of 2e to the 3x plus 1 minus 1/2 natural log of 7x minus 2. I'd like you to get to the point with your logarithmic properties to do it like that. My trick that I teach my students in 126, so if you have me, you might remember it, but if you had someone else from Math 126, anything that's in the numerator is positive or added, anything that's in the denominator is subtracted. And then exponents can be brought out front. So that's my little trick for doing that. And then I'll leave that for you guys to work through. The answer should be, I'll write it during the break, and we'll get through those two. Okay, so we got a little bit more and then we get started. Okay, cool. All right, I'm going to write the answer in the break, but let's take a break. Let's come back at 10:04. Let's come back in time. 10:14, and then we'll pick up from there. People watching the recording, go do some guided meditation. All right, we're back. So this is the answer to that one. If you'd like to jot it down or take a picture or whatever, we're going to move forward from that in just a moment. So the next two, I would like you guys to do these ones yourselves. So go ahead and work through these ones. I will slowly fill in the details and or help students out as they have questions. So I'm going to pause the recording for a moment. Okay, so I've got the answers up here. So this first one, it is a chain rule because it's a quantity being raised to the 7th with a quotient rule on the inside. So the outer function is the 7th power. So by the power rule, it would be 7 blank to the 6th. But in this case, it would be 7 of the quantity x squared plus 1 over x cubed plus 2x minus 3 to the 6th times the derivative of the inside. If you want to go straight to the answer, you're more than welcome to do so. I will give you full credit on the exam if this is what you write on the box without writing that middle step. That's fine. But that's a quotient rule. F prime is 2x, G prime is 3x squared plus 2. So it's F prime G minus G prime F all over G squared. And don't try and simplify that, it's unnecessary. All right. Any questions on that? And then the next one is a product rule, but the product rule has two chain rules in it. The first thing has a chain rule because it's e to the quantity 4x squared. So by the chain rule, derivative of the outside function, derivative of e is itself, so it's e to the 4x squared times the derivative of the inside function, which would be 8x. And then g is tangent of natural log of x, so that's a chain rule as well. The derivative of tangent, the outer function, is secant squared of x, but in this case, it's tangent of natural log of x, so it's secant squared of natural log of x times the derivative of natural log of x, which is 1 over x. So writing it all nice and neat, f prime g plus g prime f, so f prime g plus g prime, which I've written as over x, but you could write it as secant squared of natural log of x times 1 over x times e to the 4x squared. It's fine. I just wanted to write it nicer without having to make it longer to write out. Okay? Any questions? We're vibing. Okay. So as I said during the work time, I will go through these problems to I'll make a video on these two just so we can get this problem and the next problem just so we can get started with implicit differentiation. But some good problems here in the exercises, very, very good. And we'll go ahead and get started on implicit differentiation. So as we've seen in all the other parts, we've learned a bunch of rules on how to deal with every type of function. But what happens if you don't have a function? What if we have x squared plus y squared equals 25? And like with anything we did in the other problems, it was like you could find the derivative to use it and find the slope of a tangent line. But I'm given this circle, which has the graph below. And my question is, did I not bring those notes? No, I didn't. Okay, cool. So I forgot what I wanted to write that first part. Yeah. Okay. But even though I don't have the equation of a function, I can still draw tangent lines to that, right? I can draw a tangent line right here. I can draw a tangent line right here, a vertical tangent line. That's a little weird, but I can do it. And then, heck, I can even do it at 3 comma negative 4. 3 comma negative 4 right there. I can draw a tangent line. But how could I do that? Now, there's a fun rule that we could do in pre-calculus to figure out how to draw a tangent line. It's pretty interesting. You can draw a ray out of the to that point and find a perpendicular line. And that would be one way to get past that. But I want to use calculus. So we would hope that we'd be able to use calculus to do that. Now, there is some options. What we could do is we could write the function of the circle as a function in two pieces. So we have y squared equals 25 minus x squared, which we take the square root of both sides. And don't forget about the plus or the minus, right? When you take the square root of both sides, mathematically, you need the plus or the minus. So we end up with two functions. We have f sub 1 of x, or I'm going to call it f sub u, which is the positive square root of 25 minus x squared. And we have f sub l of x, which is negative square root of 25 minus x squared. The f sub u meaning the upper part of the graph and f sub l meaning the lower part of the graph. So that at least allows me a way to write that function, the circle as two different functions. And then what I can do is say, okay, 3 comma negative 4, that's in quadrant 4. So we'll use the second function. We'll use f sub l of x, which is negative square root of 25 minus x squared, which I already know I'm going to need to rewrite in radical format because I'm going to be taking a derivative. 5 minus x squared to the 1/2. So This means I can find the equation of the tangent line by finding the derivative and plugging in the x value to find the slope and call it good. So f prime sub L of x would be -1/2 times 25 minus x squared to the -1/2 times -2x by the chain rule. Inner function is 25 minus x squared. Outer function is the 1/2 power. So it's going to be that negative sign sticks around out front, and then 1/2 25 minus x squared to the -1/2 by the power rule times the derivative of the inside, which would be -2x. And that would end up being positive x over square root of 25 minus x squared. A little bit of algebra going on here. Because it's -1/2 power on the 25 minus x squared, that's the same thing as 1 over square root 25 minus x squared. And then the -1/2 and the -2 cancel, and that's where I get that. So f prime sub L of 3 is 3 over the square root of 25 minus 3 squared, which ends up being 3/4. And that's our m subtan. Slope of our tangent line. We plugged in the x value to get a specific value of the derivative. When the derivative is evaluated at a value, it becomes the tangent line slope at that specific x value. And we already have the point. So we have the equation of the tangent line. We already have the point 3 comma -4. So point slope form is y minus y sub 1. So it's y plus 4 equals m 3/4 times x minus x sub 1 minus 3. And that is the equation of our tangent line. So that would be one way to do it. However, that only worked out because like any questions on that? Let's before we move on. That only worked out because it was really nice and neat. We were able to solve for y in terms of x. We were able to get this at least into 2 equations, 2 functions. But that's not always the case. If you look at these 2 examples here that I've written, x squared plus natural log of y minus e to the x sine y equals the square root of x plus y to the 7th. Try and write that in terms of y. I'll give you a hint, it's not possible. It's not without a computer helping you along the way heavily. Or the same thing with the y cubed plus y squared minus 5y minus x squared cosine x equals 1 over xy. There's no easy way to write that explicitly. So let's, as 1 second, just to understand the terminology. If I say something explicitly, that is being very, very clear about what I'm saying. Whereas if I say something and I'm implying it, it means you need to read between the lines, correct? That's what it means to imply something. So if I say, like, if I'm talking to a person and say, ooh, look at the time, the implication is I want to leave, right? So the fact of the matter is, with these 2 equations that I've written down here that are really, really complicated, there is no way to explicitly write y in terms of x. But if you look at the graph, just like we looked at above, there is always a way, there should be a way to kind of break it up into 2 pieces. Even with a curve that looked like this. Maybe there's a swoop to whoop and like that. What I can do is I can probably break it up into maybe this piece, and then I'll do another piece here. Well, it probably needs to, like, maybe there's a piece right here that I can define it as, and then there's another piece here that I can define it as. And then it goes to here, and then a new piece from here to here. So there is a way, even if I can't actually do it, even if there's no way to mathematically do it, there should be some magical, like that there is, like, let me restate that. even if there is no way for me to algebraically get it to be the fact that it's y equal, y sub 1 is this piece, y sub 2 is the orange piece, y sub 3 is, there still is possibility for that to happen. So what I'm saying is that you can think of y as a function of x implicitly. Y is implied to be a function of x. That's the idea here. So, as such, if we think about that, we can assume that every function has y as a function of x. So you can think of it as y of x. And so we can still do this whole thing with a new process called implicit differentiation. So we're going to start off with this example and we'll go back to the other example in a second. We'll use this example, y cubed plus y squared minus x squared equals 5y minus 4 to follow along the process. So first and foremost is you're going to differentiate the entire equation, the entire thing. Differentiate the left side, differentiate the right side. Otherwise, we're not doing something mathematically possible. So I'm going to write it. Let's make sure I do what I want to do. Okay, yes. So this is the way I typically write this down. D dx of the left-hand side equals d dx of the right-hand side. Now, this is for our note-taking purposes. You don't have to write this step when you're on an exam. But this is a good step when we're starting out to understand what's happening. We're taking the derivative of both sides. Now, as an aside, I see students sometimes write this. That is gibberish. In mathematical verbiage, that is gibberish. Writing the ddx after the fact is like writing a natural log. Right? We don't write natural log here because natural log is an operation on something and we read left to right. So ddx is an operation on something, so you can't put the ddx here. Is that clear? ddx is on something, just like a limit is on something. It's limit of blank. It's ddx of blank, not blank ddx. So it's ddx of both sides. So this side has the y cubed plus y squared minus x squared. And it says 5y minus 4. And I'm going to write down what the answer is without explanation, and maybe you can see what happened. So it's going to be 3y squared dy dx plus 2y dy dx minus 2x equals 5 dy dx. Okay. That looks weird. Understandably so. Keep in mind the variable we're differentiating with respect to. We're differentiating with respect to x. So they're all separated by addition and subtraction. So we can treat each piece separately. This is the derivative of y cubed. This is the derivative of y squared. This is the derivative of x squared. This is the derivative of 5y, and the derivative of 4 is 0. So why is it 3y squared dy dx? It's an excellent question, Bianca. I'll explain it right now. So d dx of y cubed. We're thinking it's implied that y is a function of x. Somehow we might be able to actually turn y into a function of x. If we were given enough time and enough computing power, we would be able to find a way to write y in terms of x. So this is really d dx of the quantity y of x cubed. Y can be thought of as a function of x. And that's a chain rule. So write that down and let's explain it again. Notice the variables here. That's key. This is d dx of y cubed, not d dx of x cubed. So when I do this, the outer function is the third power and the inner function is y of x. So so it'll be 3y of x quantity squared times y prime of x. Derivative of the outside, which is the third power, times the derivative of the inside, y prime. And then just writing it nicely, that's 3y squared dy dx. Since it's implied, we can get rid of the y of x. Now, if it helps you at first, that's fine. Here's why I recommend against that. There's two, and this is why I like Leibniz notation a lot for this. So you can use y primes. I will not stop you from doing that. And you can rewrite them as y of x's. However, you might notice that it becomes really, really confusing very quickly. This starts to look like y times x. And this starts to look like y to the first power. So you can do it, but if you're going to do that, if you're going to use y primes, I highly recommend like doing some color coding something. Like rewrite the y primes in a different color so that it's very clear what's a y prime and what's a y to the first power. Does that make sense? So you can do it. I typically avoid it, even though it does take more time to write it as dy dx. I find it to be helpful that way. So that's the same reason why the derivative of y squared is 2y dy dx. So we can even do that one over here to show another one. Hopefully that'll help illuminate it a little bit better. So d dx of y squared, well, y is being implied implicitly. It's implicitly defined as a function of x. So this is, instead of y squared, this is d dx of the quantity y of x squared. Y is a function of x. So by the chain rule, the outer function being the second power, inner function being y of x, it will be 2 times y of x to the first power times dy dx, the derivative of the inside. Or let's write it as y prime of x, excuse me. Which we will then rewrite as 2y dy dx. And then 5y, the derivative of that, it's just the derivative of y of x. What's the derivative of y of x? Y prime. As opposed to, and I think we have enough space to even write this one here, d dx of negative x squared. Notice that the variable is the same. This is a derivative of x. It's not a derivative of y or anything like that. It's d dx of purely stuff of x. So that's just why it is negative 2x. Now, here's the cool thing, by the way. Here's the cool thing about why Leibniz notation is so nice. You can technically write this in Leibniz notation. It's going to be negative, like if you think of it as a power rule, then it's going to be dx times dx dx, if you really wanted to. Don't write this down, but just to see it. But what's dx over dx? It's 1. It cancels. Because it's not a fraction, but it's kind of a fraction, but it's not a fraction, but it's kind of a fraction. So that's where like the Leibniz notation followers actually had a much better time with this understanding. So that is the big difference. It's d dx of x squared here, where it's d dx of y squared. X versus y situation. Is that okay? Any questions on that? Much like with chain rule, this takes practice. So that's the first step. You've now differentiated the entire equation. Now you're going to isolate the dy dx terms for the non-dy dx terms. Convention is to bring everything to the left, all the dy dx terms to the left and the non-ones to the right, but it doesn't matter. If you decide to do it in the opposite version, your answer will just be off by 2 negative signs in a numerator and denominator that will cancel each other out. And I will be looking for that. So it's okay however you solve it. I'm going to bring everything to the left-hand side. So we get 3x squared, sorry, 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. I brought the dy dx terms to the left, the non-dy dx terms, of which there's only one, there's just the minus 2x. So I added 2x to both sides and subtracted 5 dy dx from both sides. Now that I've done that, all the terms on the left all have a common factor of dy dx that can be factored out front, and then we can solve. So dy dx, I'm going to factor that out front and get 3y squared plus 2y minus 5 equals 2x. So at the end of the day, dy dx is equal to 2x divided by 3y squared plus 2y minus 5. Any questions on that? It's tough at first, absolutely. I'm not saying it's easy by any means, but it's all chain rules. That's all it is. If you can remember, if you can think about the fact that it's implied that y is a function of x, even if you're struggling with it, rewrite it on the side like I did. Rewrite it as y of x or f of x if y of x makes it look too confusing. Think of y as f of x, because remember, y and f of x are synonymous. And then take the derivative of that, and you'll see that every single time it gets into the right formula. So, a couple notes about this process. All the rules that we know and love can be applied. So we can still have product rules, we can still have quotient rules, we can still have chain rules, all that stuff. And much like the chain rule, you need to practice it. Now, we're not going to have too much time to go into this one yet, so we'll practice it after, because right now we have our quiz on Wednesday that's going to be on 2.4. So it's only 2.4. So practice it tonight, practice it after class today if you have a chance. Just do one problem. Just one tonight. Like one after class, 2 tonight, 3 tomorrow, please. Please. And so the last note is that because now we can find derivatives in a different way, we can still find the equations of tangent lines. We can find where they're horizontal. We can find higher order derivatives. We can do all the stuff that we already knew and more. So let's do this last example. So instead of having to find two functions, determine which function to use, we could do it differently. So we need the slope. And the way we're going to do that is we're going to ddx both sides. We're going to differentiate both sides of the equation. So ddx of x squared plus y squared equals ddx of 25. I promise we'll be able to finish this one in 2 minutes. The derivative of x squared with respect to x is 2x. The derivative of 2y. Y is a function of x, so that's really y of x quantity squared. So by the chain rule, it's going to be 2y dy dx. And the derivative of 25 is 0. In practice, by the way, if you want to, in practice, all you do is take the derivative like you would take the derivative of x and then just stack on a dy dx at the end. That is correct. That is what happens. But I'd rather you understand the intuition. Y is a function of x, so it's y squared is y of x quantity squared. So that's why it's 2y dy dx. And then we get the dy dx's by themselves. So we get 2y dy dx equals negative 2x, which gives us dy dx is equal to negative x over y. Because I'm going to divide both sides by 2y. The 2's cancel like that. That is the tangent That is the derivative. And the derivative is used to find the equations of tangent lines. And specifically, it's used to find the slopes. But this is in two variables, but that's okay. I gave you the location. I gave you 3, -4. So dy dx evaluated at 3, -4, meaning that I'm plugging in 3 for x and -4 for y, gives me -3 over -4, which is 3/4. And I have my slope. And so I can get my answer, which is y plus 4 equals 3/4 times x minus 3. Took about the same amount of time here, but that's only because we could find the equation explicitly in that first problem. But this one, we didn't have to we didn't have to do any graph theory to figure out looking at the graph to figure out which quadrant it's in or anything like that. We could just go straight to it. That'll do it for today. Please prepare for that exam, that quiz on Wednesday on 2.4. And then we'll pick up with we'll finish off 2.5 and hopefully go through 2.6 that day as well. Okay, guys? Yes. Tentatively at this moment it is, depending on how long, how much it's going to take to get through 2.7. So, all right. Exam redos are due on Wednesday as well, so make sure you get those finished if you haven't already. Yes.
Next Monday, exam for the one on the app.
Next Wednesday is when the exam is scheduled. At least tentatively. Unless anything goes crazy and we don't get through enough material in time.
So it'll be next Wednesday's as of now.
As of now, as of right now, it is on. No, it's not Monday. Goodness.
That's what I was wondering.